So, dear students, in this video, the motivation is basically to obtain the larmor frequency, and uh, and it's also called as Larmor's theorem or Larmor's formula. And and to start with, if we go back to the one electron atom or one electron like atoms, what we obtain uh, from uh, from the Bohr model point of view, we have a postulate that this L is n h by 2 pi, where this L is the angular momentum and h is the Planck's constant. And this n is an integral number, and this number is, it cannot be zero, it is 1, 2, 3, and so on and so forth. Now, so we will have, for different principal quantum numbers, we will have the angular momentum as for n equal to 1, so we can write down the reduced Planck's constant here, and this h bar is h by 2 pi. So we are going to have the values of L. We will have h cross, 2h cross, 3h cross, and so on and so forth. But when we go into the domain of Schrodinger's, when we go into the domain of Schrodinger's picture, what is important in the wave mechanics is that the angular momentum, this angular momentum, it does not depend on the principal quantum number. It does not. It does not depend on principal quantum number n. But this angular momentum, it depends on a quantum number known as orbital quantum number. Orbital quantum number. So what we have here is that this angular momentum of the revolving electron, it depends on the orbital quantum number. And solving Schrodinger's wave equation for hydrogen atom, what we have this L, which is angular momentum. This L is under root of L times L plus 1 h cross. This is 1. And this L is the orbital quantum number, and the value of this L can be 0, it can be 1, 2, and so on and so forth. So if we go with this set of equation, we will have the values of L as 0 for L equal to 0. For L equal to 1, we will have under root 2 h cross. For L is equal to 2, we will have under root 6 h cross, under root 12 h cross, and so on and so forth. Now, what is important here is that we assume an electron revolving, and this revolving electron is an equivalent current loop. And if I assume that the charge of this electron is E, and what we do is we apply the magnetic field in the z direction, and applying magnetic field in the z direction. So here what I have an electron revolving in a loop, and this revolving electron in a loop is equivalent to a current loop. And if I assume that the mass of electron is small m, and the charge of this electron is E, and if I go back to the definition of magnetic moment, since this electron is revolving in a circular loop, it has orbital magnetic moment, and that magnetic moment is defined as the product of the current, because this revolving electron is equivalent to current into the area of this loop. So I can write down here mu L is current times A. Okay. Now, if I go with the basic definition of current, what is current? Current is rate of flow of charge, and if I use it for the current situation, uh, here what I'll have current is the charge is here the charge of electron, and to make a one complete circle, to complete one orbit, it takes a time equal to capital T, and this capital T is called time period. So we have time period here. All right, and so if I move a little bit further from here, uh, now I have this electron revolving, and it has a speed, and that speed is the distance that it travels in the whole cycle. That distance is simply 2 pi r. If I assume that r is the radius of this orbit, then uh, the time that it takes to complete that loop is t. So this t, what is the time period? It's going to be 2 pi r by v, where this v is nothing but the magnitude of velocity. And I can use the value of this t in this equation, so I'll get I equal to e by 2 pi r, and this v will go up. Okay, so this is the value of current, and I can write down this orbital magnetic moment. I can write down this orbital magnetic moment, and what will be that? That orbital magnetic moment is going to be, this is mu L. So this mu L is going to be current, and current we have evaluated. This is EV by 2 pi r times A is the area of the loop, and the area of the loop is pi r square. All right, so the point is that what we have here is the cancellation. This square and r will cancel, pi and pi will cancel, and my mu L will be EVR by 2. And I can write down this as EMVR by 2m. No problem. This MVR is nothing but orbital angular momentum. So this is E by 2m times L. Now if I write this equation in vector form, this mu L as a vector will be minus, since the charge of electron is minus, E by 2m L vector. And this equation is an indicator of the fact that this mu L, the orbital angular, sorry, or the orbital magnetic moment of the electron, its direction is opposite to the angular momentum of the electron. So they are exactly opposite. So if this is mu L, this is L. Okay, so now this E by 2m, this E by 2m, we can have the ratio between this mu L and L, and that ratio is simply E by 2m. If we go with this equation, we can write down that mu L by L is it's E by 2m. And this E by 2m is called as gyromagnetic ratio. So This E by 2m is called as gyromagnetic ratio. And 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 if I write it back into its original form, this mu L is E by 2m L. Now I would like to start things from here. Okay, so I'm taking the magnitude, and what's the value of this L from Schrodinger's point of view? This L is under root of L times L plus 1 h cross. So if I substitute this value of L in equation 1, then mu L is going to be E by 2m under root of L into L plus 1 h cross. Now this is m here, keep that thing in mind. So this mu L is E h cross by 2m and under root of L times L plus 1. Now this thing that we have here, which is E h cross by 2m, it's all made of constants, and this is what's called as Bohr magneton. This E h cross by 2m is called as Bohr magnetron. So what we will have here is mu b, and this mu b is E h cross by 2m. So this is E h by 2 pi m. And its value in SI system is, when you give the value of charge of electron, say it is 1.6 times 10 to the power of minus 19, then we have 6.63 times 10 to the power of minus 34 joules second, divide by 2 pi, that's 3.14, times mass of the electron, that's 9.1, times 10 to the power of minus 31 kilograms. This mu b comes out to be 9.24 times 10 to the power of minus 24 ampere meters. And we can write down this, what we call as, we can write down this orbital magnetic moment in the units of Bohr magnetron. And if I go back to that equation, where I have this mu L is, what is mu L? So this thing is mu b. So I would like to write down mu b under root of L times L plus 1. So the small l is the orbital quantum number, and this L is, it can be 0, it can be 1, and so on and so forth. So I'll have mu L in the units of Bohr magneton. And I will have, for 0, I will have mu b. The first one, for 1, it will be mu b under root 2. And for 2, 2 plus 1 is 3. 3 2s are 6. So this is mu b under root of 6, and so on and so forth. Now, what is important here is that we have a situation that we are supposed to apply the magnetic field in the z direction. And what this magnetic field causes, what it causes basically is we have an orbiting electron, and we apply the magnetic field in the z direction. Okay, and the radius of this electron's orbit is small r, and this is the direction of magnetic field. And let us have the projection of orbital angular momentum. Say this is L, and you have an orbiting projecting it this way. This is now, we assume this is L, and this is the z direction, and join the center of this circle, and assuming this angle to be theta, and here we will have dl, and this whole thing is L, all right, and this angle is 90 degree. Now if this angle is 90 degree, this radius of this orbit is going to be L sine theta, all right, and this is dl, the small angular momentum change in small change in angular momentum, that's dl, all right, and this is the direction of magnetic field that's applied on this revolving electron, and this L is the orbital angular momentum that's being projected, and there is the precession. As you apply the magnetic field to the orbiting electron, it presses the orbital angular momentum of this system, and and we have those symbols out there. We can see them. Now, what is important here is to talk about the torque. And what is torque basically? Torque is tau, and this torque is simply mu L cross B. Now, B is the magnetic field that's applied along the z direction of this revolving electron. And this torque is a vector quantity, and this torque is basically the rotational replica of force. The role that's played by force in translatory motion, the same kind of role is played by torque in rotational motion. Now this torque is a vector quantity, so I'll put a vector here. So mu L is a vector and B is a vector. Now, if I write down the magnitude of this torque, and from vector point of view, it's quite clear that this torque is perpendicular to the plane of mu L and the magnetic field. So if I write down the magnitude of this torque, this magnitude will come out to be mu L B sine theta. Right. So that's the case, that this torque, that the torque that this system will experience will be given by mu L B sine theta. Now, if I go to this situation, what I have here is dl. Okay, so it has to be capital dl. Now we have an arc type of situation. We have an arc type of situation, and this arc is dl, and this length is how much? It is L sine theta. So how much is this? So this dl is L sine theta times this angle. So dl is L sine theta times d theta. Okay, so so what is this d theta? I can write down angular frequency. Omega is d theta by dt. So this d theta is omega dt. Now I can use the value of this d theta in this equation. What am I going to get is dl is equal to L sine theta. For d theta, I'm going to write omega dt. Right. Now I can write down here so I can write down that this dl by dt is L sine theta omega. Now, we better understand that torque is also defined as the time derivative of angular momentum. So if torque is also defined as the time derivative of angular momentum, then instead of dl by dt, I would like to write torque here. So that is L sine theta omega. Now this is the omega. This is the omega of precession. This is the precession. This is the Larmor's frequency that we are interested to develop an expression for. And what we have torque here. This torque is mu L b sine theta. If this is my equation A and this is my equation B, I would like to equate the two equations. So what's going to happen is this L sine theta omega will be equal to mu L b sine theta. Mu L b sine theta. And we can see here this sine theta and sine theta is going to cancel. So what will be omega? Omega will be mu L by LB. Now this equation is our target, and this equation is known as Larmor's formula. And this equation gives us the measure of the frequency, angular frequency, that precess when you are applying the magnetic field to an electron orbiting in a circle. And this orbiting electron is also carrying magnetic field, and when we apply the external magnetic field on it, there is a precession, and the frequency of that precession is omega, and that omega is directly proportional to the applied magnetic field. So if you are increasing the strength of the magnetic field, then automatically the Larmor angular frequency also goes on increasing. It also increases. So omega has a direct dependence onto the application of magnetic field, and this Larmor formula it plays a vital role in explaining the phenomenon like Zeeman effect. And other points of interest are always there in atomic physics where this Larmor formula is used.